we move on to our next talk, which will be given by Hironobu Fukuzawa from Tohoku University in Sendai. And the title is Nanoplasma Formation by High-Intensity Hard X-rays.
Thank you for introduction. First of all, I would like to thank organizers to give me an opportunity to talk about our research at this great conference. I will talk about nanoplasma formation from rare gas clusters by high-intensity hard X-rays, namely X-ray free electron laser from Sakura. This is outline of this talk. After an introductional part, I will talk about the experiment, and then I will talk about two results about argon clusters and xenon clusters. Then I will summarize this talk. So as for introduction, one of most expected experiment using XFL is single-shot X-ray diffraction experiment. Although the target species will be destroyed by irradiation of XFEL, since the XFEL pulse duration is very short, one can expect to get image before destroyed. However, we are questioning what would happen in the target species during the XFEL pulse, and is there no effect to diffraction pattern? And in the case target species is atoms, we found the following. We used xenon atom as a target and used 5.5 keV XFEL, which is above L-shell threshold of xenon atoms. We measured ion time of flight spectrum and observed high charge state up to plus 26. And this is typical pathway to produce xenon 24 plus from theoretical prediction. First, xenon atom absorb X-rays and L-shell will be ionized. Then OJ cascade occurs. Then second photon is absorbed and OJ cascade and so on. So we found photoionization and sequential electronic decay cycles are repeated multiple times within the XFEL pulse duration. And the next example is for small molecule. We used methyl iodine molecule, and again we used 5.5 keV X-rays. So this is schematic drawing of iodomethane, and in this molecule only iodine absorb X-rays. And we measured momenta of fragment ions in coincidence, and we get correlation of momenta. And this is the example of the correlation. Horizontal axis shows charge state of iodine, and different color indicates different charge state of carbons. The vertical axis is ratio of carbon momentum and iodine momentum. The symbols are experimental results, and lines indicates model simulation. So our model simulation will reproduce the experimental results. And from this model simulation, we found within 10 femtoseconds, hydrogen atoms released from molecule almost completely, and distance between iodine and carbon increased 10%. For detail, please refer this our recent publication. And let's go to the target molecule on this talk, that is clusters. First, let's think about irradiation by laser, intense laser, not XFL. After laser irradiation, many atoms in the cluster are ionized. Then nanoplasma is formed when the electrons ejected from atoms trapped by Coulomb potential of multiply charged cluster ion. So this phenomenon is well known in the infrared region to EUV region. Then now question is nanoplasma also formed by intense hard X-ray pulse irradiation? And if so, how is nanoplasma formed? Okay, next I want to show our experimental technique. So we did experiment at spring-gate Ångström compact free electron laser, namely Sakura. The length of Sakura is about 700 meter, but 700 meter is compact in the community of XFEL. And the Sakura is located not at the underground, but at the top of the mountain. And typical parameter of XFEL light for user operation is like that. We can get photon energy range from 4.5 keV to 15 keV. And repetition rate is so far 30 Hz, but it will be 60 Hz. And pulse, we can get pulse energy of about 300 microjoule at 10 keV, and pulse duration is less than 10 femtoseconds. Okay, this is the schematic drawing of our experimental setup. So XFEL goes in this direction, and XFEL pulse is focused using KV mirror, and then introduced in our reaction chamber. And after our reaction chamber, the pulse is go to atmosphere and measured intensity by PIN photodiode. In this presentation, I used XFL of photon energy of 5 and 5.5 kV, and bandwidth was 60 eV. And this experiment, the repetition rate was 10 Hz. And at the focal point, focal size is about 1 to 2 micrometers, and peak frequency of XFL pulse was about 50 microjoule per micrometer squared. And cluster beam was introduced as a pulse supersonic gadget to the focal point like this. This is a picture of our cluster source. The rare gas clusters were prepared by adiabatic expansion of the rare gas through 250 micrometer nozzle at room temperature. We used argon and xenon in this work. And by controlling stagnation pressure, we can get this value of average cluster size. Although we used this source at room temperature, potentially this can be cooled down to make a big cluster or different kind of clusters. Okay, this is a picture of our charged particle spectrometer. It's consisted with several electrodes and tubes. And we equipped 2 sets of position sensitivity detectors. This spectrometer can be used as ion time of flight spectrometer, or 3-dimensional ion momentum spectrometer, or electron or ion velocity map imaging spectrometer, depending on the purpose. Actually, we used time of flight spectrometer for experiment with atoms, and 3-dimensional momentum spectrometer for molecules, and velocity map imaging spectrometer for clusters. I will show about this mode. This is velocity map imaging mode. I applied up to 27 kilovolts for electrodes. And I made distance between reaction point and the detector as short as possible to collect high energy electrons. And using this configuration, we can collect electrons emitted into copper strontium with kinetic energy up to 1 keV. And these three sets of lines indicates the electron trajectory of 100 TeV, 400 TeV, and 900 TeV. Now, we have to pay attention. Since I put detector as close as possible, now electron trajectory is different with respect to microchannel plate surface. And as a result, trajectories of some electrons are parallel to the slanted capillaries of the MCP, like this. This makes detection efficiency low. And this is low image of electron detection. We used circularly symmetric electron emission, but you can see there is a low intensity region at here. And to investigate this phenomena, we did some electron trajectory simulations. And this shows relationship between position on the detector and the angle. Angle is defined by electron trajectory direction and MCP's capillary. And this point is indicating the 180 degree. It means electron trajectory and capillary is parallel. And the position of 180 degree and low intensity region is fit. So using this simulation, we could compensate image like this. Now we can get cylindrical image. Okay, next I would like to show our experimental results. First, I show about argon clusters. So this is experiment and theoretical electron spectra of argon clusters. So blue lines is experimental result, and solid red line is theoretical results. And theoretical results is come from Zoltan Jurek and Robin Santor group at CFER. This is electron spectrum of atoms. At around 200 eV, there is LMMOJ. And these are results from for clusters at different cluster size. With increasing cluster size, plateau at this region is produced. This is interpreted like with increasing average cluster size, stronger potential builds up. Then the electrons are decelerated and the plateau is produced. And also we found a strong peak at zero energy. This strong peak is due to the thermal emission from nanoplasma. And this is the time evolution for the theoretical electron spectrum. First, during the X-FEL pulse, this blue line and this black line, only the proton is being formed. The strong peak at 0 eV developed after the X-FEL pulse. like this. This is interpreted. After the XFL pulse, the ionic system has started to expand and let some of trapped electrons escape from the nanoplasma. And, this is entire electron energy spectrum of argon 1000. In the experiment, we can measure up to here. But we are using 5 keV XFL, and argon KH is 3.2 keV. So K-shell photoelectron has about 2 kilo electron volts, and it should be here. And there are another electrons from OJ and valence. But in this spectrum, we can see the emitted electrons are decelerated about 500 electron volts. Then let's see the measured spectrum. So we expect LMMOJ should be at here in the case of atom. But in this case, because electrons are decelerated, the contribution of LMMOJ should be like that. And also there is a contribution from LMMOJ and should be like this. And thermal emission from a nanoplasma is contributed like that. And if nanoplasma is formed from only LMMOJ and LMMOJ electron trapping, the amount of electrons is not enough to make this huge intense peak. And again, with the help of theoretical prediction, we found the majority of the trapped electrons are created by impact ionization caused by low energy OJ and secondary electrons. So I think this is important because this secondary electron creation is occur at everywhere. Okay, next I want to go to xenon clusters. So this is electron spectrum of xenon cluster with average size of about 80. Now we used photon energy of 5.5 keV, and the peak clearance is about 55 microjoule per micrometer squares. Since xenon L edges are like that, we expect L2 photoelectrons and L3 photoelectrons appear at here, and we see the peaks around here. And also, MNNOJ from xenon atom has about 500 eV, and we also observed peaks around 500 eV. Now I will increase cluster size. Then we got these spectra. We found with increasing average cluster size, the valley between the peaks becomes a plateau, like that. This is also interpreted by the deceleration from deceleration by the Coulomb potential created at the cluster. And we also found thermal emission from nanoplasma. And from experiment, we can also get asymmetry parameter beta for these photo emissions. And it is plotted as a function of electrokinetic energy. We found the beta values are almost zero, except at the photoelectron energy region. And now to make clear, I averaged the beta value within the photoelectron region and got like this. So vertical axis is the beta value and the horizontal axis is average cluster size. We found the beta values for both L2 and L3 photoemissions decreases with increasing average cluster size. It is due to electrons are scattered by atoms in the cluster. Okay, next I want to show the peak fluence dependence of electron spectra. This is measured using 5.5 keV XFL and average cluster size of 10,000. This spectrum is the same as this red line. Now I will reduce peak fluence and got this line. And we found that shape of the spectra does not significantly change with the changing peak fluence. And the strong peak at zero energy here is observed even in the case of peak fluence is the lowest, 2.5 microjoule per micrometer squares. So this peak fluence corresponding to, in this peak fluence, xenon atoms in the cluster can be ionized, only 5%. But still we can see the fingerprint of nanoplasma. So this means the nanoplasma is efficiently produced due to the Auger cascade. And this slide shows beta parameter. And this plots averaged beta parameter with respect to peak fluence. We also found the beta values for photoemissions decrease with increasing the peak fluence. So far, we do not interpret this phenomena. Okay, let me summarize my talk. So we have investigated electron emission from argon clusters and xenon clusters by XFL from Sakura. And in case of argon clusters, electron emission are Auger emission decelerated by the Coulomb field of highly charged parent clusters. And the secondary electron emission appears in form of thermal emission evidencing the nanoplasma formation. And in case of xenon clusters, electron emissions from L2 and L3 photoemissions and MNN and Auger emission, and also strong thermal emission evidencing nanoplasma. Only L2 and L3 photoemissions have angular distributions. That becomes more isotropic with increasing cluster size. Okay, of course, I cannot do this kind of research only by myself, and I have many collaborators. Some of them are attending this conference. And this is a picture of experimentalists and theorists. And thank you very much for your attention.